Machine learning, once a niche term, now a buzzword shaping our world. At its core, it's about teaching computers to learn from data, not by rigid rules, but by example. Just like showing a child many pictures of cats until they recognize one on their own. Machine learning algorithms do this at scale, finding patterns in oceans of data. Data analytics is its essential partner, the process of collecting, cleaning, and transforming data into insights we can act on. If machine learning is the student, data analytics is the school that prepares it. These fields drive everything from Netflix recommendations to early disease detection. Instead of relying on human intuition alone, we now use machines to uncover patterns too complex for us to see. It's a collaboration. Human ingenuity meets machine intelligence. In this series, we'll start with the basics of data analytics, then build up to advanced machine learning, always grounding concepts in real-world examples. The goal: a clear, intuitive understanding of how these tools work and why they matter in our data-driven society. Before machines can learn, we must first understand data, its language. Data analytics begins with descriptive statistics, tools to summarize and sketch the main features of a dataset. Measures like mean, median, and mode reveal what's typical. Range and standard deviation show how much things vary. Standard deviation in particular tells us how tightly data clusters around the average, crucial for spotting outliers or volatility. Visualization is key. Charts like histograms and scatterplots reveal patterns hidden in raw numbers. These tools help us explore, ask questions, and form hypotheses before building models. For example, a retailer can use descriptive stats to see average monthly sales, spot the peak month, and measure sales fluctuations. A simple line chart can reveal trends at a glance. This isn't prediction, it's the factual foundation for all future analysis. Descriptive analytics turns chaos into clarity, setting the stage for machine learning. Once we understand our data, we can move from describing the past to predicting the future. Enter regression. Regression analysis examines relationships between variables, letting us predict one, like house price, from others, like size or location. Linear regression draws a straight line through data points, modeling the trend. Simple, yet powerful. The model is trained on historical data, adjusting itself to minimize prediction errors. Not all relationships are straight lines. Polynomial regression handles curves, but the goal remains: map inputs to outputs as accurately as possible. A classic use: predicting house prices from features like size, age, and location. The model learns, for example, that bigger houses usually cost more. When a new house is listed, the model estimates its value based on learned patterns. Regression is the backbone of predictive analytics, turning data into actionable forecasts. It's how we move from what happened to what's likely next. The process of minimizing error is at the heart of how machine learning models learn. Regression is where data starts to become prediction. Decision trees bring human-like logic to machine learning. They predict outcomes by learning simple rules from data, branching like a tree from root to leaf. Each node asks a question, like, is income above $50,000? And each branch leads to a decision. The beauty is transparency. You can trace exactly how a decision was made. For example, a bank's loan approval tree might first check income, then credit score, then loan size, ending in approve or reject. The tree learns which questions to ask by finding splits that best separate the data, using metrics like information gain. This process repeats until each path leads to a clear decision. Decision trees are prized in fields where explaining why matters, like medicine or finance. They turn complex data into simple, understandable rules. With decision trees, machine learning becomes interpretable and actionable. A single decision tree is easy to follow but can be unstable, overfitting quirks in the data. The solution: build a random forest. An ensemble of many trees, each trained on random samples and features. Each tree votes, and the majority wins. Errors cancel out. making predictions more robust. Randomness ensures diversity among trees, preventing any one feature from dominating. Random forests are used everywhere, from medical diagnosis to fraud detection, because they're accurate and reliable. For example, hundreds of trees might each assess a patient's risk, and the majority vote gives a trustworthy diagnosis. Ensemble learning like this leverages the wisdom of the crowd. Random forests turn many weak models into one strong predictor. Support vector machines, or SVMs, are all about drawing the best boundary between classes. Imagine separating red and blue dots with a line. The SVM finds the line with the widest margin between the groups. The closest points, called support vectors, define this boundary. If the data isn't linearly separable, SVMs use the kernel trick to project it into higher dimensions, where a clean split is possible. SVMs focus only on the hardest to classify points, making them efficient and powerful. They excel in tasks like image and handwriting recognition, where boundaries are complex. For example, distinguishing between handwritten 3s and 8s by finding the optimal dividing line in high-dimensional space. SVMs are precise, robust, and effective for clear-cut classification problems. They're the go-to tool when you need sharp, reliable separation. K-means clustering is unsupervised learning, finding structure in unlabeled data. The goal group similar data points into clusters, like sorting fruit by type without labels. You choose the number of clusters, K, and the algorithm iteratively assigns points to the nearest center, then recalculates centers until stable. It's simple and fast, but sensitive to initial placement and the choice of K. Methods like the elbow method help pick the right number of clusters. A classic use, customer segmentation. Grouping shoppers by behavior for targeted marketing. K-means reveals hidden patterns, letting companies tailor strategies to each group. It's a first step in exploring new data, uncovering natural groupings. Clustering turns raw data into actionable segments. LSTMs, long short-term memory networks, bring memory to machine learning. Traditional neural networks forget the past. LSTMs remember, making them ideal for sequences like language or time series. Each LSTM unit has a cell state, its memory, managed by gates that decide what to keep, forget, or output. This lets LSTMs capture long-term dependencies, like remembering the subject of a sentence until the verb appears. For example, in translation, an LSTM reads a French sentence, encodes its meaning, then writes the English version, preserving context and nuance. LSTMs power tools like Google Translate, making translations more natural and accurate. They're also used in speech recognition, stop prediction, and more. The key LSTMs learn what matters over time, not just in the moment. They've revolutionized how machines handle sequences. With LSTMs, deep learning becomes context-aware. Memory is now part of the machine's intelligence. We've journeyed from simple averages to memory-driven neural networks. What unites these tools is the power to learn from experience, turning data into insight, prediction, and action. Machine learning isn't about artificial consciousness. It's about practical tools that recognize patterns at scale. These algorithms optimize supply chains, personalize feeds, discover new drugs, and fight fraud, quietly shaping our world. But with power comes responsibility. We must address bias, transparency, and privacy. Models reflect the data they're trained on. If the data is biased, so are the predictions. Ensuring fairness and accountability is a societal challenge, not just a technical one. Mastering machine learning means asking the right questions and interpreting answers responsibly. This field blends statistics, computer science, and domain expertise, offering a chance to solve real-world problems. The journey is steep, but the view is transformative. You can help shape our algorithm-driven future.